In a previous video, I showed you how to calculate the optimal size of the capacity between two areas. In this video, I will expand the problem. I will not only look at two price areas, I will look at, first of all, 3 areas and then a much larger number of areas. As a starting point, I will use the example 848 in the textbook Fundamentals of Power Systems Economics. On the basis of this example, I will show you how you can apply the power market simulator to optimize the transmission capacities between a number of price areas. The learning objectives there are: you must understand section 8.4.8, transmission expansion in a meshed network, in the textbook Fundamentals of Power System Economics. And you must know how to use the power market simulator to optimize the size of connections between several price areas. The content of this video is that I will give a short repetition of section 8.4.8, and then I will recalculate the example in the textbook using an Excel sheet. And finally, I will show you how to optimize interconnectors between price areas using the power market simulator. But let us start looking at the textbook. Here we have the system we will calculate on here. We have a node A, a node B, and a node C. We can see here that there is a demand here in node A, which is in fact equal, the load here is equal to 0. And we have a demand here in area C, which in the period 1 is 2,500 and 10,000 in period 2. And we can see the demand here in area B. This is the values here in period 1 and period 2. We can also see here that we have a generator connected to A, to B, and to C. We can see here the maximum capacities of these generators, and we can see the marginal cost curve for these generators. And finally here on this slide here we can see the cost of building interconnectors between the 3 areas here, with the K, the length here, and the capacity of the connector. When we do the optimization of how to build the most optimal interconnectors here between the 3 areas, we have this objective function here. We want to minimize the total costs here, and it is the cost over the 2 periods we are working with here, at period 1 and period 2. This is the hours in the period. This is 8,760 hours per year. And this here is the integral of the marginal price curve here, giving us the total price curve for each area. So we minimize the total production costs here, taking into account that we also have to build connections here, and this is the yearly price of average price of building connectors here between A and B, and between A and C, and between B and C. And then we have a lot of constraints here. One constraint is that the export from A to B and from A to C plus the demand in area A should be equal to the production in area A. And the same here for area B and for the area C, and all the transfer between, the total sum of transfer between the areas should be equal to 0. And then this is for period 1, this is for period 2. And then we also have a constraint concerning the capacities, that we must not exceed the maximum capacity of the line between A and B, and we must not exceed the maximum capacity between of the line A and C. These figures here is the same as the values up here, and we must not exceed the transmission capacity of the line ABC. And here we say that in the maximum, we will not exceed the maximum capacity of the generators in period 1 and in period 2. In the optimal solution here, we can see the flows. First of all, we'll see here that we have a higher demand than production in area B, so there will be a transport from A, and there will also be a transport from A to B, and there will also be a transport from C to B, because we have a higher production than demand in area C. And you can see the optimal flows here will be the flow here from A to B will be 1963 megawatt, and here the flow here will be 576 megawatt, and the flow here will be 1387 megawatt in this direction. And here in period 2, you can see the flows that will go here, and in this period here we have in fact we need production here, because we have a much higher demand than production here. We also have a higher demand than production here. So this node here will supply both B and C. And you can see the optimal flows here in the two, in the three lines. Here we calculate the total production costs in generator A, B, and C in the different price areas. In order to do so, we will integrate the marginal price equation and then calculate the total cost. The total cost they are multiplied with 0.25 here, because 1/4 of the time of the 8,760 hours is in period 1, and here we will multiply the cost with 0.75, because 3/4 of the time will be in period 2, so that we can add these here, and then we will get the total cost for an equivalent hour here. And here you can see the total cost for an equivalent hour in both period 1 and period 2. This figure here is multiplied with 8,760, and we will get this value here. This is the total cost for a year. What we also can see here is that this here was the flows in the lines. This here is the maximum flow. That this is the optimal capacity of the interconnectors here. And when we multiply this capacity with the functions telling us how much the yearly cost will be per megawatt hour, we get this value here. That is the investment cost measured in dollars per hour. And when we sum up all these costs for the three interconnectors here, we get this sum here in dollars per hour. Now we go and look at the nodal prices, the area prices, and we can see here that there is a different area price between the three areas, both in period 1 and in period 2. So there will be bottleneck incomes in all the periods here for all the lines. And what you also can see here is that when we calculate the amount of money that the generators will receive here in period 1 and how much the producers will pay here in period 1, then we can see that there is an excess amount of money, and this excess here is equal to the bottleneck income. And this here is also the bottleneck income from period 2, and when we add these two together, we get the total bottleneck income. And this bottleneck income is when we have this optimal transmission lines here, the equivalent hour bottleneck here is equal to the capacity cost, the yearly cost of having this capacity. When you do the calculation of marginal cost here, you can see that there's a small error in the textbook, because this value should be 11.68, this value here. What is interesting here is that even if the flow here is not maximum, we have a much higher capacity here, so we could say, okay, let us now send much more power from A to C so that we could have the same price in the two areas. But we cannot do that, because if we try to increase this value here, this value will also increase. And this here is in fact the maximum capacity on the line from A to B. So we cannot just say, okay, we want to send more from A to C in order to get the same prices in the two areas, because this would affect the power flow on the transmission between A and B, and it is already at its maximum. Normally we would say, okay, if if the transmission capacity is not reached, then the prices in the two areas would be the same. But this is not true when we are also considering the power flows in the system. I will show you this in the next slides. In this slide here, we have the same system as before, and now we make the assumption that the voltage in each of the nodes here are the same. We have the same voltage in all the nodes here, but the voltage angle is not the same. When we assume that, we need only to consider the reactance of the lines here. So this will make it more easy to do the calculation. And in the textbook we assume that the reactance of these lines are the same. So the reactance of this line is equal to the reactance of this line and the reactance of this line. So when I'm trying to export 100 megawatt power from A to B, 2/3 of the power will go through directly from A to B, and 1/3 of the power will go through node C to reach node B. We also need, in the textbook, we also need to export some power from C to B in this first period. And when we do that, 2/3 of the power will be exported directly from C to B, and 1/3 will go through node A here to B. Let us now look at the textbook example. In this case, we have a production here that should be exported both to B, because we need to have power, more power in node B, but we can see here that there is also an excess amount of power here in node C, so some of the power that is needed in B here, node B, will also come from node C. But we start here with saying that now we want to export this amount of power to node B, and 2/3 of this amount here will go through this line. This is equal to 1693 megawatt, And this amount here will go through node C to B. We also need to export from node C to B because we have an excess here. This is the production, this is a consumption, so there's an excess amount of power here that should be exported to node B. And when we look at that, we know that 2/3 of it will be directly exported and 1/3 will go through node A here. And when we look at the total capacity need here in this example here, we can see that the total utilization of this line here is 1963 megawatts, and this line here is this amount here, and this line here is this amount here. And when we go back to the textbook here, you can see that these flows we have calculated here is exactly the same as in the textbook. So this is the way the textbook optimize the transmission lines between these areas.
When we are calculating market prices, without considering the physical flows in the transmission lines between the bit zones, we call it normal trading capacity calculations, NTC calculations. When we consider the physical flows, we need to have a way to calculate the flows. And in order to do that, we will use a power transfer distribution factors matrix. This matrix here is shown in a 3 by 3 matrix here. Later on in this video, I will show you how this matrix is calculated, but here I will show you how it works. If I, for instance, say here that in the area A here, we will have an export of 1 here to area C, you can see that the line between A and C will have a flow of 1. If I say here that there will be an import to area B of, for instance, 10 here, then you can see here that there still will be an export of 1 from A, and then now there will be an export from C of 1 to area B. And here you can see the flows in the system. The flow here from C to A will be 3 here, and together with the one that is produced here in A, there will be a flow of 4 from A to B, and the flow from C to B will be 6 here. If I insert the flows from the textbook here, it was 2539 here, and it was minus 3350 here. Then you can see here we will get the exact same flows as in the textbook. So this here is the power transfer distribution factors matrix, and this matrix will show you how the physical flows will be in the system if you have different export imports in the different nodes in the system. I will now show you how the power transfer distribution factor matrix is generated. We have here a 3 by 3 node system with also three transmission lines between the nodes. In order to simplify the calculation, we assume that the reactances here in the lines, they are the same in all three lines here, and this means that the substances, they are also the same. We start here with setting up the substance matrix, and then the way we do that is that there are two lines out of V1, and they're going to VE2 and HI. The two lines out of VE2, they go to VE1 and HI, and there are two lines out of HI going to VE1 and VE2. So this here is the substance matrix. We have, in order to calculate the power transfer distribution factor matrix, we have to have the reactance matrix. In order to do that, we need to invert this matrix. We cannot invert this bus substance matrix. So in order to to calculate the reactance matrix, we define one of the nodes as a slack node. And in this case here, I've defined HI as the slack node. And then we have a 2 by 2 matrix that is easy to invert. I've inverted the matrix here, and as you can see here, it's just inverting this matrix here. We have these values here. When we've done that, we set in the slack node here, and then we have the bus reactance matrix here, where HI is the slack node. Now we have the bus reactance matrix, and then we have to look at the line substance matrix. And you can see here we have the three nodes and we have the three lines here. And the line between VE1 and VE2 is going out of VE1 and into VE2. The line VE1 to HI is going out of VE1 to HI, and this line here is going out of VE2 to HI. And now we are ready to calculate the power transfer distribution factor matrix. We just have to multiply the line substance matrix with the reactance bus reactance matrix, and then we get this matrix here, which is the power transfer distribution factor matrix. Here we have the power transfer distribution factor matrix here, and the only thing I have to do now is I have to calculate the export import out of each of these nodes here, and when I have calculated this export import, then I can multiply this vector here with the power transfer distribution factor matrix, and then I'll get the flows, the physical flows in the system. This slide shows how the power transfer distribution factor matrix is incorporated into the power market simulator model. I'll not go through all these formulas here, but just show you here that we have the object function here minimizing the total cost. We have this condition here ensuring that there will be an energy balance in each of the nodes. And we have this condition here, where you can see this here is the export import from each node, and it is multiplied on this matrix here, and this gives the flows in the system, and these flows has to be between the capacity limits in the system. When we have optimized this system here, after that we can calculate the nodal prices in the system using this formula here. Before we calculate the example from the textbook using the power market simulator, I will make the same calculation here in the Excel sheet. And what you see here is the values of the marginal cost curve for unit in A, in unit in B, and the unit in node C. And this here is the cost of the transmission lines between the different nodes here. And this here is the number of hours in period 1 and the number of hours in period 2. These values here is the load in each of the different nodes here in period 1 and in period 2. These values here is the production in period 1 of power unit A, B, and C, and this is the same values for period 2. These values is taken directly from the textbook. But what we do here now is we calculate the production cost here. And in order to calculate the production cost, we will integrate the marginal cost curve here, and then we get a second degree polynomial. And when we insert the values here in the second degree polynomial, we get the production cost in period 1 for unit A, B, and C, and this is the cost per hour. And here we calculate the marginal cost in period 1, 2, and 3, and this is also done using these values here up here. We do the same for period 2, the production cost and the marginal cost here, and then we calculate the production cost per hour for the two periods here. So what you can see here is that we multiply the price per hour with the number of hours here, and then we divide with the number of hours in a year. So here we have the total production cost in for unit A for per year, per hour per year, and here we have it for B, and here we have it for C, and this here is the total cost for all three units. And now we're going to calculate the transmission cost. This here is the flow between the different nodes. It's also taken directly from the textbook. This here is the capacity here, and when we calculate the transmission cost, we use this transmission capacity and multiply it with these costs here, and then we get a per hour cost for the line AB, and the per hour cost for line AC, and the per hour cost for line BC. And this here is the total cost for all three lines here per hour. And if we add the production cost and the transmission cost, we get this value here, which is the total cost, including both production and transmission per hour. This figure here you can also find in the textbook. We now calculate here the income for the producer in A and the income for the producer in B and C. And as you can see here, the way we do that is that we multiply the production here with the marginal cost in this period here, and we multiply that also with the number of hours and divide it with the number of hours in a year. So we get a value per hour, and this is both for period 1 and period 2, and we do the same for the producer B and the producer C, and then we calculate the cost for the consumers in A, B, and C, and the cost is the consumption multiplied with the marginal cost here. This value here is the difference between what the producers they receive and the consumers they pay, and this value here is the bottleneck income or congestion income for the TSO in the system. We'll now go up here and look at also the congestion income. If we calculate the congestion income for the line AB in period 1, it is the difference between the marginal costs here multiplied with the flow. This is this value here, and this value here we also we divide it with 4 because it is only 1/4 of the time that we are in period 1. We do the same for the line AC here. the difference between the prices in the two areas multiplied with the flow, and we get this value here, and we divide it with 4. In period 2, we do the same here, but now we divide it with 0.75 because 3 of 4 parts of the time we are here in period 2. And then we add all these incomes here, congestion incomes, and get this value here. And as you can see, this is exactly the same as this value we calculated here. So the difference between what the consumers they pay and the producers they receive is the same as the bottleneck income. I'm now inside the education version of the Power Market Simulator, and I will show you how we can recreate the results shown in the textbook using the Power Market Simulator. We have here V1, which is the same as node A in the textbook. This is the same as the node B in the textbook, and this is the same as the node C in the textbook. So if I click here, this is the unit in node A. It is approximated with all these units here. So instead of having a straight line, we have a staircase curve. If I click here, you can see that the first step here, this here is a unit with a capacity of 200 megawatt. And when the production is 200 megawatt, the marginal cost here you can see is 2.6 euros. And here, this unit here is also have a capacity of 200 megawatt. And when we have a total production capacity of 400 megawatt, the marginal cost will be 3.5, which is the same as in the textbook. For in VE2, which is equal to node B, we also have approximated the straight line marginal cost curve with this staircase curve here. And when we look here, the first unit here is a 200 megawatt unit with, and when we have a total production of 200 megawatt, the marginal cost will be 1.95 euros. And when the capacity is 400 megawatt, the marginal cost will be 2.55 euros, which is also the same as in the textbook for unit in node B. And finally, in HI, the unit in node C is approximated with this staircase curve here, where we also have the first unit here has a capacity of 200 megawatt. And when we have a production of 200 megawatt, the marginal cost here will be 2.35 euros, which is the same as in the textbook. These hours here is P1, and these hours here is PE2. So we start here with P1, and I make a calculation clicking on these 3 areas, make a flow-based calculation, and here you have the marginal prices in the 3 areas. I will save these values here, and then I will also save the values here for the total production. This is the production in V1, and this here is the transmission surplus here. We also save this value here, and I do the same here for VE2, save the production and the transmission surplus, and I also do that for HI, the production and the transmission surplus. When I've done that here, I make the same calculation for period 2 here, flow-based calculation. Click on the 3 areas. flow-based calculation here and save the nodal prices here and also the production and transmission surplus. And now I have done these calculations here, I will return to my PowerPoint. Now I will compare the results from the textbook and the results from the Power Market Simulator model. And if you look, we start here, look at the production here in the P1 period here and the period 2 here. And this is the values from the Power Market Simulator model. And these values here is from the textbook. As you can see here, the values, they are nearly the same. The flows here will of course also be the same if the productions here, they are nearly the same. The flows will also nearly be the same. If you look here on the area prices from the Power Market Simulator, you can see that these values here, they are different from the values in the textbook. But this is due to the fact that we have approximated the straight line marginal cost from the textbook with a staircase curve in the Power Market Simulator. If I make a correction for the staircase curve here, then the values coming from the Power Market Simulator model will be the same as the values in the textbook. If we look here on the bottleneck revenues here, this is the values from the Power Market Simulator model here, and this is the corrected values here. And when we compare the corrected values with the values in the textbook, you can see here that the values, they are nearly the same here. These values here is the values that you can compare with the values in the textbook. What we've seen here is that the Power Market Simulator gives the same results as the results in the textbook, so that you can use the Power Market Simulator in order to make flow-based calculations. I'm now back in the Power Market Simulator because I want to show you the difference between making a normal trading capacity calculation and a flow-based calculation. We calculate here for period 1. Click on the 3 areas, and then I make a flow-based calculation. And as you can see here, we have the same prices in the 3 areas as you had seen before. If you just look at this here, all these prices, and remember the prices, then I do a normal trading capacity calculation here. And then you can see here the price here in V1 is the same because there's no changes here. But you can see now the prices in VE1 and HI, they are becoming the same. And that is due to the fact that the model, they believe that you can send a lot of power from V1 to HI in order to have the same prices in the 2 areas. When I click here and say show results here for V1, you can see now the production here is 2,852 megawatt here, and before it was 2,400 megawatts. So we have an increased production here, and this increased production is transferred to HI, where we have a smaller production here. You can see here now the production is only 2,989 megawatt. So the price here, the marginal price has decreased here, and it has increased, and it is the same in these 2 areas. So there is a clear difference between making a flow-based calculation and making a normal trading capacity calculation. Now I will repeat the calculations, but on a more realistic example. I've chosen to calculate here on Germany, France, Switzerland, Austria, and Italy. And again, we simplify, assuming that there is the same reactances in all these lines here. We start here with making the bus substituents matrix the same way as we did before. We have out of uh, Austria here, we have 3 nodes going to Switzerland, Germany, and Italy. And out of Switzerland, we have 4 nodes going to Austria, Germany, Italy, and France. And this is the way we construct the bus substituents matrix. And then we say that the France should be the slack node, and then we have a 4 by 4 matrix here. We invert this 4 by 4 matrix here and get this inverted matrix, and then we insert the slack nodes in the inverted matrix, and then we get the bus reactance matrix with slack. After that, we calculate the line substituents matrix. So we have all the lines here, and then we say that this line here is going out of Austria to Switzerland. This line here is going out of Austria to Germany. And this is the way the line substituents matrix is constructed. And then we now are ready to make and calculate the power transfer distribution factors matrix here. It is the product of the line substituents matrix and the reactance bus reactance matrix here. And here you have the power transfer distribution factors matrix for this system here. These values here are put into the power market simulator model, and now I will show you the results when we are calculating flow based on these countries here. Now I'm inside the experimental version of the power market simulator, where it is possible both to calculate flow based and normal trading capacity calculations. I click here on France, Switzerland, Italy, and Austria, and then I make a flow-based calculation here. You can see here the marginal prices in the different bidding zones here. And if I do a normal trading capacity calculation here, you can see here that the values, they are the same in all these areas here except for Austria. If I click here on Switzerland here, you can see that this is the demand in Switzerland, and this here is the production. So this nuclear power plant that is the price setting unit in Switzerland when we do a normal trading capacity calculation. If I make a flow-based calculation here and click on Switzerland here, you can see that this is again the same demand, but now the production is much less, and it is these units here that is the price setting units. So this means that when we're doing a flow-based calculation here, we cannot export the same amount of power out of Switzerland as we do in the normal trading capacity calculation. So you can get very different results when you do a flow-based calculation compared with a normal trading capacity calculation. In the remainder of this video, I will show you how you can also include optimization of transmission into your calculation. In a number of models, optimization of transmission connections can be directly included in the optimization. This is done by including the cost of transmission in the object function and making the capacity also a variable. in the power market simulator, this is not possible. So if you want to optimize also the transmission connections, this is done by manual iteration. And I will show you how this is done in practice. I'm going to show you how you can iterate and find the optimal transmission lines using the power market simulator. In order to do that, I used the case from the textbook here, and I'll start up calculating the first guess using an Excel sheet. Here you have the load in period 1 and 2 in the three areas here, and we have the production capacity. And my first guess would be a guess where we will have the lowest values of the transmission capacities. So I say here where we have the very high load in B, I say that we will have the maximum use of the production capacity in area B. I set this to 7,000, and in the period 2 here we have the maximum demand here in C. I set the maximum production in C to 8,000, and then the other values I've not tried to optimize. I'm just assured that the sum of the production is equal to the demand in the two periods. And then here I calculate the for this period 1, I calculate the export from area A here, and this here is the import to area B, and this is the export for area C. And when I multiply this vector here on the power transfer distribution factors matrix here, I get these flows here. And in the other case here in period 2, I multiply these values here and get these flows here. When I make this here as the starting guess here, I can say that in this line here, the line V1 to V2, if I have a maximum capacity of 1800 megawatt here, then it is possible to transport the flow that I need to transport. And if I have a capacity of 900 megawatt here on the line between uh, V1 and HI, then it is possible to transport the power that is needed to be transported in this line. And if I have a capacity on this line here from V2 to HI of 1200 megawatt, it is possible to transport the needed flow. So I use these as my first guess in the calculation. And then I go and make a power market simulator calculation using these capacities here. Now I'm inside the education version of the power market simulator. And what I'm going to do now is that I will change the capacities of the different lines here, the line between V1 and V2 here. It should be, as my first guess here, it should be 1800 megawatts here. And I save this here. And my first guess of the transmission line between VE1 and HI should be 900 megawatt here. Save this. And the capacity between V1 and HI here should be 1200 megawatt. And then I make a calculation here where I say flow-based calculation, and for each of these areas here I save the production and the total production cost here for VE1 and for VE2 and for HI, and also the total cost here for all three areas. The total production cost for all three areas here in this period. And when I've done that here, I do the same calculation for period P2 here, flow-based calculation. And again, I save the production here and the production costs here for each of the three areas, and the production cost for all three areas totally. And then now I return to my PowerPoint. Here you can see the capacities of the first calculations we've done. This was the first guess. And here I will insert the production in period 1 and period 2 for three areas, and the flow of power between the areas here for period 1 and period 2, and the total production cost here in period 1 and period 2, and the total cost per year here with this capacity. So I insert the values here from the Power Market Simulator model, and I can see here that this here is the total cost for my first guess here. And then I make a new calculation where I set the capacity of this line here up with 200 megawatts. So now it is 2000 megawatts, and I can see here this is the values from the Power Market Simulator model. And what I can see here is that the total cost they increases, so that production cost they have reduced. But if I also include the price of having this higher capacity here, the total cost will increase. So it is not a good idea to increase this capacity here of this line here. And then I make a new calculation where I've increased the capacity here of the line V1 to HI, put and set all the values from the Power Market Simulator in here. And now I can see that the total price costs here have reduced. And then I do the final calculation here where I've increased the capacity of this line here with 200 megawatt, and I have all these values from the Power Market Simulator model, and I can see that now the total cost they have increased. So it is a very good idea to increase the capacity of this line. So I do another calculation here where I increase it up to 1500 megawatts here, and you can see that still the costs they have been reduced. So with this capacity here, it is still a good idea to increase the capacity of this line. I continue these calculations here, and what I can see here is that when I come to this here, this is the case with these capacities here. I will get the lowest value of the total cost per year. And if I compare that with the result from the textbook, we had these here, these capacities in the textbook. You can see that the total cost, they are nearly the same, and the capacities of the lines are nearly the same here. So it is possible to use the Power Market Simulator model to make an iterative optimization of transmission lines. So if you, for instance, want to calculate the optimum capacity of a line between two areas in a system, You can use the power market simulator and change the capacity of these lines until you get an optimum. In this video, I've shown how to interpret the textbook example on optimizing transmission capacities. I've also shown how to take into account the physical flows between bidding zones in practice using power transfer distribution factor matrix, and how to calculate the power transfer distribution factor matrix. And finally, I've shown how you can use the power market simulator model to calculate optimal transmission capacities between different bidding zones. Thank you for your attention.